Hello, and welcome to Submodule 2.4, the last module in AC analysis. In this module, we're going to study the transformer, but first, we have to understand a couple of concepts that are central to how transformers work. The first one is the concept of mutual inductance, how the magnetic field couples between inductors. And we're also going to calculate voltages and currents in circuits containing mutual inductances, as well as calculating the energy stored in the system. Let's start by talking about a circuit with an inductor that is made up of N turns. We know that if we force a current through that inductor, we're going to generate a magnetic field. And the total magnetic field or linkage is going to be the product of the number of turns in that inductor times the magnetic field. We also know that in linear systems, such as the circuits that we are treating in this course, the magnetic linkage is also the product of the inductance of the inductor times the current that is being forced through it. So we have those two equations: magnetic linkage, total magnetic field, equal to the number of turns in the inductor times the magnetic flux, and that is also equal to the inductance times the current that is going to flow through the inductor. So what we can do is use those two equations from physics and write that the magnetic flux is equal to the inductance divided by the turns in the inductor times the current. And that gives us this equation here. We also know from physics that the voltage induced in an inductor is the time derivative of that total magnetic linkage. And since we already established that the magnetic linkage was equal to the inductance times the current, then differentiating the product of the inductance and the current, we get that the voltage is equal to the inductance times the time derivative of the current plus the current times the time derivative of the inductance. Now we're working here with non-time varying devices, so it is safe to assume that for our inductors, the inductance does not change over time. So in this term, the derivative is going to be 0. So this is going to be 0. And we are left with our familiar equation that says that the voltage in an inductor is equal to the inductance times the derivative of the current. And we have seen this before in previous submodules. Now what happens when we have two inductors and we put them side by side such that the magnetic field couples around the two windings? We're going to call this the primary winding with N1 turns, and over here on the right, the secondary winding with N2 turns. So we can force a current on the primary, and we're going to have an induced voltage on the secondary. We can write equations like we had before for each side, and we have that the magnetic linkage on the primary side is equal to the number of turns on the primary times the magnetic flux, and that is of course equal to the inductance of the primary winding times the current on the primary. Similarly, we have that the magnetic linkage on the secondary is equal to the number of turns of the secondary winding times the same magnetic flux that is going to couple from the primary to the secondary. And we assume that all the magnetic flux is coupled from the primary to the secondary. We can also write that the voltage in the primary is the time derivative of the linkage in the primary, and that is going to be equal to the inductance of the primary times the time derivative of the current in the primary. Now, to analyze what voltage we get on the secondary, we can start by writing that the voltage in the secondary is going to be the time derivative of the linkage in the secondary, which is the time derivative of the number of turns in the secondary times the same magnetic flux. So substituting the magnetic flux that is generated from the primary and coupled into the secondary as the inductance of the primary divided by the number of turns of the primary times the current of the primary, we get this equation over here. And we take the derivative of that. And towards the right of this equation, we can follow the results to this expression, which is the ratio of turns in the secondary to the primary times the inductance of the primary times the time derivative of the current in the primary. That is going to be the voltage that is going to be induced across the secondary windings. We can call this expression, the ratio of the turns times the inductance in the primary, the mutual inductance of the system. So once we establish that, again, we have that the linkage in the primary is equal to the inductance of the primary times the current in the primary plus the mutual inductance times the current in the secondary. And also that the linkage in the secondary is equal to the mutual inductance times the current in the primary plus the inductance of the secondary windings times the current in the secondary windings. And applying the voltage equation to that, or in other words, taking the time derivative of the linkages, we have these final equations. That says that the voltage in the primary is equal to the inductance in the primary times the time derivative of the current in the primary plus the mutual inductance times the time derivative of the current in the secondary. On the secondary side, we can say that the voltage induced on the secondary is going to be the time derivative of the linkage, the magnetic linkage on the secondary, and that is going to be equal to the mutual inductance times the time derivative of the current in the primary plus the inductance in the secondary times the time derivative of the current on the secondary. And we also established that the mutual inductance, whether you look at it from the primary to the secondary or from the secondary to the primary, are equal, and we're going to call that term M for mutual inductance. Now something happens regarding the polarity when the turns in the secondary and the primary do not have the same direction. We're going to get that the current are going to flow in the opposite directions from secondary to primary. And to account for that, we write that the magnetic linkage in the primary is equal to the inductance in the primary times the current in the primary minus the mutual inductance times the current in the secondary. Similarly, the linkage on the secondary is going to be minus the mutual inductance times the current in the primary plus the inductance in the secondary times the current in the secondary. And again, if we take the derivative of those linkages to get the voltages in the primary and secondary respectively, we have the following equation, which is the same that we saw in the previous slides, but now we have minus signs in front of the mutual inductance terms. And this shows a picture of a primary winding with a different winding direction on the secondary. We also denote a difference in winding direction by putting a dot on one side and putting another dot on the opposite side, but down in the lower side of the winding. So in this case, we have that the windings have a direction such that the polarities on each side, primary and secondary, are the same, and we have positive signs in front of the mutual inductance terms. And then, or when we have a situation where the windings in the primary and the secondary are such that the polarity of the voltage in the secondary is the reverse of the polarity of the voltage in the primary, we put a dot on the opposite side of the secondary winding, and that corresponds to the equations where we have minus signs in front of the mutual inductance terms. We also can express the relationship of the voltages and the currents in mutually coupled coils for AC circuits in steady state. And we studied those in previous submodules, and we know that those are the ones where we have sinusoidal signals and all the signals in the system have the same frequency. So in vector form, we can say that the voltage in the primary is equal to j omega times the inductance of the primary times the current vector in the primary plus j omega times the mutual inductance times the current in the secondary. Similarly, we have that the voltage in the secondary is equal to j omega times the mutual inductance times the current in the primary plus j omega times the inductance in the secondary times the current vector in the secondary. Note that the current vectors are going to take care of the minus signs for the mutual inductance terms depending on the polarity on the secondary with respect to the primary. Since the currents are vectors, they will have a direction and an angle as well that will take care of the difference in polarities. Now let's do an energy analysis for coils, for mutually coupled coils. If we start with the equation for power as the product of the voltage and the current, and we know that on the left side, on the primary side, we can write the voltage as the inductance times the derivative of the current times the current. We can integrate that power and we get an equation that we had already seen, which was half the inductance times the current squared. That is the energy stored on the left side, on the primary. And since we have conservation of energy, we can say that the same energy is delivered completely to the right side. So the energy on the right side is half the inductance of the secondary times the current squared on the secondary. Now we also know that the voltage in the primary is equal to the inductance of the primary times the derivative of the current in the primary plus the mutual inductance times the derivative of the current in the secondary. And if we do that integration again of the power, we get that the energy is equal to the mutual inductance times the product of the currents. So the total energy stored in the network is the energy stored in the primary, the energy stored in the secondary, plus the energy due to the mutual inductance. And if the coil configurations are different, we simply have a negative sign in front of the mutual inductance term. And this is the final unified equation for the energy stored in two mutually coupled coils. We have the primary energy, the secondary energy, and the energy due to the mutual inductance. Another way of writing the equation above after some manipulation is this, where we can define a constant K, which is the ratio of the mutual inductance to the geometric mean of the inductances of the primary and the secondary, where that K term is going to be between 0 and 1 inclusive. Now let's learn about the ideal transformer. If I have some type of magnetic conductive medium, like a core of iron, and I have a winding on the left side, and I call this the primary, and I have another winding of N2 turns on the right side, and I'm going to call this the secondary, and because of the dots are on the same side, we know that it has the same configuration. Since this is a highly magnetically conductive structure or material, I'm going to have a concentration of magnetic flux flowing around this structure. And I already know that the voltage on the primary is equal to the number of turns in the primary times the derivative of the magnetic flux. Similarly, on the secondary, the voltage is going to be the number of turns on the secondary times the derivative of the magnetic flux. Ampere's law requires that the magnetic field intensity is 0 around the closed path through which it is flowing. That yields that the number of turns in the primary times the current in the primary plus the number of turns in the secondary times the current in the secondary is equal to 0. Which gives me the equations of the relationships for voltage and currents in a transformer. So I have that the ratio of the voltage in the primary to the voltage in the secondary is proportionally equal to the ratio of the number of turns in the primary to the number of turns in the secondary. Therefore, I'm always going to have a higher voltage on the side that has the higher number of turns. If I have more turns on this side than on the secondary, then I have a step-down transformer. And if I have a smaller number of turns on the primary than in the secondary, then I have a step-up transformer. The current, however, follows a different direction such that as the number of turns goes up, the current goes down in the winding to keep this equation balanced. So the higher the number of turns on one side, the lower the current. If I have higher number of turns in the primary than in the secondary, then the current in the secondary is going to be higher. Similarly, if I have lower number of turns in the primary than in the secondary, then the current in the secondary is going to be lower. Also remember that to keep the conservation of energy, since we have the number of turns fixed, if the voltage goes up, if the voltage goes in one direction from primary to secondary, then the current must go in the opposite direction from primary to secondary. And we have the same type of results for the vector voltages and currents for steady state AC circuits. We can also define a constant nu as the ratio of the number of turns from secondary to primary. So this ends this module where we learn about mutual inductance, turn ratios. We calculated voltages and currents in circuits containing mutual inductances, talked about the analysis of energy in mutually coupled coils, and finally we also looked at voltages and currents in ideal transformers.